Good morning and welcome to this postgraduate video course on advanced hydrology. In the last class, we looked at a couple of methods of fitting a probability distribution to a given set of data. And the methods we had looked at were, the first one was the method of moments and the second one was the method of maximum likelihood. We looked at one example that is the same example of exponential distribution, fitting the exponential distribution using both of these methods, and we saw that the parameter lambda of the exponential distribution comes out to be 1 over x bar. And then we discussed the relative merits and advantages and disadvantages of both of these methods. Then we introduced the concept of what is called the testing the goodness of fit of a probability distribution. We said that fitting a probability distribution is like model calibration, and we would like to validate a mathematical model always whenever we do model development. We said that fitting a probability distribution basically means finding the parameters, and how good or bad these parameters are, there are many tests available for doing that or to assess the goodness of the fit of a model. So, we will get started with the assessment of or testing of goodness of fit. Okay. What do we mean by saying when we say that the testing the goodness of a fit of a PDF? It basically means that we are trying to quantify, all right, how good or bad a fit to a PDF or a probability distribution is. How do we do that? Using any test, and there are many tests available, and we said that we are going to use what is called a chi-square test. Okay. So, in this course we will look at a very famous test of goodness of fit, which is called the chi-square test. And then we said that any of these testings is like hypothesis testing, in which what do? We make a certain hypothesis or assumption, and then we calculate certain statistic corresponding to that test. Then we compare that calculated statistic with a standard statistic, all right, for certain level of confidence, and then we say that at that particular significance level or the confidence level, we either accept the hypothesis or we reject the hypothesis. Okay. So, what we will do is, first we will look at the procedure or the step-by-step method of this chi-square test, conducting this chi-square test, all right, and then we will take up one example. Okay. So, let us get started today by looking at the procedure which we can follow to conduct this chi-square test. The first step is we estimate each of the unknown parameters. We estimate each of the unknown parameters of the assumed distribution. Okay. There may be one PDF we are fitting, there may be more than one PDF we are trying to fit. So, we do that for all the PDFs, and if there is only one, we estimate the parameters, all the parameters that is of that particular PDF. The second step is we divide the data. All right. What have we done in the first step? We have used the data that is available, all right. And what do we do in the second step? We divide this data into k classes, okay, or what is called cells, and determine the probability of a random value falling within each class or cell using the fitted distribution. Okay. So, these are the first two steps in which the first step is we just estimate the parameters of the assumed distribution, all right, or we just fit the distribution or find out the values of the parameters, okay, either using the method of moments or maximum likelihood or whatever. Okay. Once we have done that, the next step is we divide the whole range of data into k classes, all right. For example, let us say you have the annual rainfall, the minimum value is 0, the maximum value is 100, we can divide it into 5 classes from let us say first one is from 0 to 20, 20 to 40, 40 to 60 and so on. Okay. So, let us say we divide the whole range of data into k classes, and then what we do, if you see here, what we are saying is after we have divided the data into k classes, we determine the probability of a random value falling within each class. How? Using the fitted distribution. Okay. So, what we are doing is we are trying to find out the probability of occurrence of the random value, all right. How? Within a particular class. Let us say there are 5 classes for the case of your annual rainfall, as I said. So, the minimum value is, let us say for a second class is 20 centimeter, second one is the higher one is the 40 centimeters. So, what we are doing is we are trying to find out what is the probability of occurrence or what is the probability of the annual rainfall being between 20 centimeters and 40 centimeters. How can we do that? Well, we have already fitted the distribution, we have the equation for the PDF, we have the equation for the CDF, cumulative distribution. Using all those, we can find out all kinds of probabilities, right. So, we can find out the probability within a range. So, that is the second step. Let us move on. What do we do in the third step? We try to find out the number of occurrences. How can we do that? We multiply each of the cell probabilities by the sample size n. Okay. So, let us say that your cell probability is Pi, all right. What is this Pi? Pi is nothing but from the basic definition of your probability, this is NA over N, isn't it? What is NA over N? NA is the number of occurrences of particular kind and N is the total number of or the sample size or occurrences, right. So, if you have the cell probability as Pi, you multiply that by N, what are you going to get? NA, which is your Pi times N. Okay. So, basically in the third step, what you are doing is determining, all right, what? The expected number of observations, and we will call this EI, okay, for each cell, all right. Each cell meaning what? I is varying from where to where? You have how many? K cells. So, I will vary from 1 to K, okay. And how do we find this number? According to the fitted distribution. Is this clear? So let me say that your E of I is nothing but the cell probability which you have determined multiplied by the total number of data points or the sample size. Okay. If I go back, what we are doing is we are multiplying each of the cell probabilities Pi by the sample size n, and then what we are saying is that that number is what? Expected number of observations in each cell. So EI is equal to what? EI is equal to the cell probability multiplied by the total number of data points that will yield the expected number of observations or occurrences of the events as per the fitted distribution, and we are calling this number as EI. Okay. Next step is number 4. From the given data, we already have the data with us, right? What we do is we count the number of observed values. We count the number of observed values in each cell. And let us call that MI. Okay. So what is this step? The fourth step is we are just counting the number of observations in each cell. Coming back to our example of the annual rainfall, let's say we have 50 years of data, 50 different values of annual rainfall, right? And then we have divided the range 0 to 100 into 5 classes. So all you then do is you take the first observation, let's say it is 22 centimeter. What you do? You just throw it in the second cell between 20 and 40, and you keep on doing that with all of them. So that way you will be able to get the count or the number of observations in each cell or in each class. From which source? From the data itself or the actual observations, right? So now you have the expected number of observations in each cell from the fitted distribution, and you have the same number by the data set. All right. So now we try to compare these two numbers M and E, okay, and calculate what is called the chi-square test. So that is the next step. Number 5, compute the chi-square test statistic, okay, as follows. That is your chi-square, I am going to put a subscript C here, which means the calculated one or the computed one from the data, all right, which will be equal to what? This is how it is defined. It is nothing but MI minus EI whole square divided by EI, where I is varying from where to where? It is varying from 1 to k. Okay. So you see that this is how the chi-square test statistic from the computed data is defined. Then coming to the next step, what we do is we always compare the computed test statistic with a standard value. All right. So then we say compare the computed value of your chi-square, right, with the tabulated values. The standard statistic is always available in standard tables. The tabulated values of your chi-square value using k minus p minus 1. What is it? This is degrees of freedom. Okay, and this is denoted as nu, let's say, and a certain significance level let us say alpha. Okay. Let me go to the next page, where what is P? P is the number of parameters estimated in step 1. Okay. And K is the number of classes we have already defined. All right. New we have defined as K minus P minus 1 as the degrees of freedom. Okay. This standard chi-square value which is tabulated, it is tabulated with respect to the degrees of freedom, that is number 1, and other parameter is the alpha, which is the significance level. It is expressed as in percentage. Normally it is 5% or 10% or 0.05 or 0.10. Okay. So, what we are doing here is we are just reading out manually the table, the value of the chi-square test or the standard chi-square value depending upon the degrees of freedom. And what is the degrees of freedom? It will depend upon the kind of problem, right, which is P minus K minus 1, where P is the number of parameters. For example, if you have fitted a exponential distribution, how many parameters are there in exponential distribution? We have seen there is only one, right. So, there is one parameter, only one parameter in the exponential distribution. All right. Similarly, the number of classes you will have 10, 20, 30 or whatever, and then you find out this degrees of freedom, you choose certain significance level and just read out the value of chi-square standard value. Okay. So, then the condition is if your chi-square for degrees of freedom certain value and alpha is greater than chi-square computed, means what? Means it is a good fit. Okay, it is as good as that. On the other hand, if your chi-square for certain degrees of freedom and significance level is less than or equal to chi-square computed, means the fit is not good. Okay. Now, as I said, a significance level is normally selected, which is either 5% or 1%. Okay. In the probabilistic terminology, there is this alpha or the significance level is also expressed as 1 minus alpha, which is the confidence level. So, sometimes we say the confidence level is equal to 1 minus alpha. Okay. So, if alpha is equal to 0.05, then your confidence level, which is 1 minus alpha, will be what? Is 0.95. Okay. Or if it is 5%, then confidence is how much? Confidence is 95%. Okay. So, this is the most popularly used significance level 0.05. Now, what I am going to do next is I will give you the guidelines for choosing this value of K. K is the number of classes. All right. And as you can see that the final result, whether your fit, the test of the fit will pass or fail, may depend upon the choice of the value of K. Why? Because the value of the standard test statistic chi-square depends on K. All right. It is K minus P minus 1. So, there are 2 or 3 different people conducting this test. Different people may take different value of K. All right. Depending upon that, the answer may be on either side. Okay. So, what we do is we try to minimize that, and there are certain guidelines that are available to choose. All right. So, let us look at the guidelines for step 2, which is choosing the number of classes K. We will look at 2 methods. All right. Method A is for the discrete distributions, okay, discrete PDFs, and method B is for continuous PDFs. These are just the guidelines. There is no hard and fast rule. All right. So, there are for different types of PDFs, the guidelines are slightly different. So, let us look at method A, or case A rather, which is for the discrete type of distributions. What does it say? I am going to write it down. The number of classes K is taken in such a manner that the number of observations, all right, in each cell as per the fitted distribution is how much? Is at least 5. That is all it says. Okay. So, what does this method say? What it is saying is that the number of classes we select in such a manner. For example, annual rainfall is between, let us say, 0 to 100. This is the range we have. We can divide it into two classes. One class is 0 to 50, other class is 50 to 100. We can also divide it into 10 classes, 0 to 10, 10 to 20, 20 to 30, and so on, right? But what this method is saying is that the guideline says that the classes should be selected such that we have at least how many? 5 observations or 5 occurrences in each cell, all right. Let us say you divide it into 10 classes, all right, 0 to 10, 10 to 20, 20 to 30, and so on. Then you find out that in certain cell or some particular cell, the number of observations are only 3, all right. What you do in that case? What we do is we combine the individual cells, all right. So, if we determine or if we find that the number of expected observations is less than 5, we just combine the adjoining cell, or we redefine our cell boundaries, okay. So, this is the method A. This is applicable for the discrete distributions only, all right. Method B we will look at for continuous PDFs. For this also there are two cases or two methods, subdivisions, okay. The first one says that the choice of K is actually arbitrary. As per this one is arbitrary when this is applicable when the number of data or observations n is very large, okay. When it is too large, actually we do not worry too much, all right, it can be arbitrary, all right, n is too large. Too large means n may be more than 200 or so, okay, that is when we say it is too large, all right. And how do we determine that? And we take or we use the following relationship in this case, okay. It says K prime is equal to 4 times of your 0.75 and n minus 1 square, everything raised to the power 1 over 5, okay. So, what we do is then we take the value of K is the nearest integer to K prime, okay. So, the first method is applicable for the cases when the number of data set is very large, all right, n is more than 200 or something, then we calculate k prime using the equation we have just seen, and then we take the nearest integer and we say that this is the value of k. All right. It is more or less actually arbitrary or empirical. All right. When we have lot of data points, then the choice of k is not very critical, because you will have lots of observations in each cell. Okay. For the second case, when the number of data set is not huge, or for moderate values of n, okay, a good rule is what? Is to make your k as large as possible, all right, subject to the restriction that it must not exceed n by 5. It must not exceed n by 5. Okay. So, what we are saying is that for the moderate number of data points for the continuous case, all right, we take the value of k as large as possible, all right, but it should not be more than n by 5. In case of our let us say rainfall, annual rainfall data set, let us say we have 100 years of data, okay, 100 data points, then what is the upper limit of the number of classes? It is n by 5 or 20. We should not have more than 20 classes, all right. Ideally, it should be between n by 4 to n by 5 or something like that, sorry, n by 5 to n by 8. Okay. Anyways, so let us move on. One important thing which we need to learn is how do we determine these cell probabilities, all right. The cell boundaries the cell boundaries are determined from the CDF, the cumulative distribution function of the fitted distribution. Okay, of the fitted distribution, that how, that is using the parameters which we have fit. As the value such that it satisfies the following condition, that is probability of your x being less than equal to x1 should be 1 by k. For the first cell, that is the probability of your random variable having a value less than equal to some x2 is equal to 2 by k, and so on, all the way to the probability of your random variable having a value less than equal to x k is equal to what? Is equal to k minus 1 over k. Okay. So, what we are saying is that the probability of occurrence, all right, is same, it is 1 by k, all right, for each cell. Using that concept, we are finding the values of x1, x2, x3, x4 all the way up to xk, all right. So, these numbers x1, x2, x3 actually function as the cell boundaries, all right. So, what will be the first one? The first one will be between 0 and x1. The second cell will be x1 to x2, third will be x2 to x3, and so on. The first and the last one are basically your the minimum value of the observed value of your random variable and the maximum value of the observed value of the random variable. Okay. So, if you want to say that the lower bound of the first cell and the upper bound of the last cell, okay, are taken as the smallest and largest values that the random variable may take upon, okay, theoretically. Okay. So, what we have seen actually is the complete method of this carrying out the chi-square test. All right, there were 4 or 5 different steps. That is what we saw first, and then we looked at certain guidelines that can be followed or that should be followed to the step 2, which is the classifying the data into k number of classes and finding the cell probabilities. So, there are certain guidelines we should follow for finding this number k. Now, what we will do is we will take up an example to demonstrate how this method actually can be implemented, or how we can test the hypothesis once we have fitted a distribution, how we can find out, how we can quantify whether this particular fit which we have found out is good or bad, or how good it is. If it is good, how good it is; if it is bad, how bad it is. Okay. So, let us look at an example. The observed times between the rainfall events at a given location are given as follows. These are the data that are given to us: 1.2, 2.4, 4.25, 0.90, 0.77, 13.32, 12.2, 9.2, 3.55 and 1.37. Okay. What we have to do is fit an exponential distribution. To these data. Number 2, check using the chi-square test if the data fit the exponential distribution adequately. Okay. So, this is the problem, or this is the question in which we are given the time elapsed between 2 rainfall events, and there are different data points given, I think about 10 of them. What we have to do is we have to find out whether first thing we have to do is we have to fit an exponential distribution, and the second thing we have to do is we have to find out whether this fit is adequate or not. All right, and then we will use a standard value of alpha, which is 5%. Okay, so let us look at the solution of this question. Okay, in which what is the random variable x? How is it defined? It is nothing but the what is called the inter-arrival times between 2 rainfall events. That is your random variable. See, what is given to us is this data. What is this? Observed times between the rainfall events at a given location. Okay, times between 2 rainfall events. Okay, so this is what is called the inter-arrival times. Okay, and this actually follows exponential distribution from the knowledge of hydrology. Okay. the inter-arrival times, it follows the exponential distribution. So, these are the data given to us. So, what we do first thing is the first part is what? Fit the exponential distribution, alright. What is the exponential distribution? Well, we have seen the PDF is given as what? Lambda e minus lambda x for all values of x greater than what? 0, right. What does this mean now? The inter-arrival times, can it be negative? The inter-arrival times, we said that the inter-arrival time follows the exponential distribution, and exponential distribution is for non-negative random variables only. And in this case, you see that the inter-arrival time, that is the time between two rainfall events, it cannot even be 0 actually. When you are defining the two rainfall events, then they have to be separated by some time. So, it has to be positive, right. So, it cannot be negative and it cannot be even 0. So, it should be greater than 0. Okay. So, that is what we are saying here. So, this is your small f of x or PDF, and we can easily find out that the capital F is going to be, if you integrate it, 1 minus e minus lambda x. Okay. And this is true for this. So, this is the equation of your exponential PDF or the distribution. Now, what we have to do is we have to determine the value of what? This parameter lambda, okay, in this first step. So, let us do that. Fit exponential PDF means what? Means find the value of lambda, isn't it? And what is lambda? We have seen yesterday using the two methods, method of moment and method of maximum likelihood. What is lambda? Nothing but 1 by x bar. So, can you find out x bar? It is nothing but the average of the data points, right. So, what you do is you just find out x bar is equal to, there are 10 data points, summation of your xi, I going from 1 to 10. What are xi's? Xi's are the inter-arrival times, they are all given to us. I am not going to spend time on that, you can find it out, it will be 4.916 days. Okay. By the way, I should mention that all these are in days, I forgot to mention that. Okay. So, this is your x bar, or on an average the inter-arrival time, on an average the inter-arrival time between two rainfall events is how much? About 4.2 days or 4.9 days or 5 days, okay, as per the data that is available to us. Now, I am going to just mention one thing here, is that this example which I am taking, it is only for demonstration purposes, okay. Remember, we have seen certain guidelines of how do we select the value of k in carrying out the chi-square test, alright, at least 5 observations in each cell and so on, right. But what we are going to do here is we will not actually adhere to those guidelines, because we have only 10 data points here. So, for demonstration purposes, I have purposefully kept the number of data points as only 10, so that the things are manageable here. And some of you may be confused that how come we are not following those guidelines. It is not the purpose of this exercise. I just want to caution you beforehand. Okay. All right. So, let us move on. Once we have found out the x bar, you can find out what? The value of lambda as 1 over x bar, okay, which will be 1 over 4.916, which will be 0.203417, and what is the unit of this? Days inverse, okay. All right. So, then your fitted distribution is what? It is this. X for all values of x more than 0, and capital F of x, the CDF, is given by what? 1 minus e minus lambda x, right, which is 0.203417 of your x. So, this is your answer to the first part, which is the fitted distribution, or you fit a exponential PDF. That is what we have done. This is the fitted distribution to the data. Okay, so the next step then is we have fitted the exponential distribution. All right, in the second part of this problem, what we have to do is we have to find out the adequacy of this fit, or the goodness of the fit of this. All right, and we are going to use the chi-square test as we have seen. All right, so in part B, we carry out the chi-square test. Okay. In the chi-square test, the first step is determination of the parameters, which we have done already, and then the next part is, or the next step is, we divide the data into k classes, right? And what I am going to do here is divide the data into 7 classes. Okay, again it is for demonstration purposes only. Okay, don't worry about how come you have 0 observations in each cell, in some of the cells, or less than 5, and so on. Okay, and what are these 7 classes? First one is less than 2 or 0 to 2. Second one is your 2 to 4. Third is, these are the inter-arrival times in days. Remember, capital X is what? That is your inter-arrival time in days. Then you have 4 to 6. Fourth is 6 to 8. Fifth is 8 to 10. Sixth is 10 to 12. And the 7th class is what? Is greater than 12. All right. So this is the class distribution we are going to follow for this particular example. All right. Now, if we move on, the next step is to find what? The cell probabilities. For the first cell, you have to find the probability such that the x is between what and what? Between 0 and 2, right? Which is nothing but your probability of x being less than equal to 2, right? What is this given by? By the knowledge of your PDF and CDF, the probability of a random variable being less than equal to a particular value, which is 2 days in this case, it is given by what? The cumulative distribution function value at x is equal to 2, right? So I can then write this as f at x is equal to 2, which is 1 minus e minus lambda x with x is equal to 2, isn't it? So this is going to be equal to 1 minus e to the power minus 0.203417 times what? Times 2. You can calculate it, and it should come out as 0.33427. Okay. So this is the cell probability for the first class, which is between 0 and 1. How can then now I find out E1? E1 is the number of expected observations in first cell, all right, as per the fitted distribution, right? This is equal to what? The cell probability multiplied by the total number of observations, which is 10, all right. So then what you do is you just find out the expected number, which will be 0.33427 multiplied by 10. So it will be 3.3427. Okay, it can be a fraction, it can be a real number, it does not have to be an integer, because we are using the fitted distribution. Let me do one more case for the cell, second cell, that is, this was for, let us say, k is equal to 1. Now we have k is equal to 2. All right. What we have to do is we have to find out the probability of the random variable, assuming what? The value between 2 and 4. From the knowledge of our CDF, we can say that this is the probability of x being less than equal to 4 minus the probability of x being less than equal to 2. It should be clear to you. Okay. What is this equal to? Well, this is nothing but the CDF for x is equal to 4 minus of your CDF for x is equal to 2. that is f at x is equal to 2. What is this? This is 1 minus e to the power minus lambda times 4, right. I am not putting the value of lambda here, minus 1 minus e to the power lambda times 2. Okay. You can put the values of lambda and you can simplify this. What you are going to get is this number 0.222521415. All right, we can chop off the digits here. That will give you E2 as what? 10 times of this, which is 2.225, okay, and so on, 225,21415. So, this way you see we can actually keep on doing this process, and the best way to carry out these computations is we always do this calculations in a tabular form. It's always a good practice to organize the repeated calculations in a tabular form. Okay. So, what you do is you create a table, on the top you write all the formulas which you are going to use, and then just arrange everything. Otherwise, it becomes very lengthy and time consuming. Okay. So, that is what I am going to do. All right. So, we arrange the calculations in tabular form. Okay. All right. So, what do we do is we have the class or classes going from 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12 and greater than 12, or 12 to infinity or whatever. Then what we have is the next number I am going to have actually is mi. What is mi? Mi is the actual observations based on the data, all right, which you can count and do that. So, this I am going to put here directly for you. So, you have 4 in the first one, 2 in the second one, then 1, 0, 1 you can verify these numbers, and then 0, and the last one is 2. The next column is the probability of your random variable x being less than equal to your, let us say, lower bound on the cell or the lower values of the cell, and the Cu for the I. Okay. I is going from 1, 2, 3, 4, 5, 6 and 7. All right. We have determined this for the first and second already. Okay. So, if I wrote that, it is going to be 0.33425, then you will have 0.222 and 52. These numbers we have found out. And the other one, I will just write it, you can verify these things. 14815, this is 0.09863, this is 0.06. 5663, 0.043755, and the last one is 0.087073. Okay. We multiply this number by 10, all right, and get what is the expected number of observations based on the fitted distribution. All right. So, this will be 3.3425, this will be 2.2252 and so on. Okay. 0.9863, 0.657, 0.438 and 0.871. Okay. I am just rounding off. Then you have the last column here, which is I am going to call chi-square component from the ith cell. Okay, contribution to the chi-square from the ith cell. What is that? This is mi minus ei whole squared divided by what? Divided by ei. Okay. So, you have the values of ei and mi. All you do is calculate this guy here. Can you do that? Sure, we can. All right. So, let me write some of these numbers. So, you have 0.12934, next is 0.0228. You can verify these numbers please. Then you have 0.1565, 0.987, 0.18, 0.437, the last one is 1.465 or so. Okay. Then the last thing we do is we sum these up, the last column that will give you chi square c, right, which is 3.37622. Okay. What is the computed value of chi square we had defined? It is nothing but the summation of what? Mi minus ei whole square divided by ei. So what we are doing is we are calculating mi minus ei whole square over ei for each cell. You sum the last column up, that will give you chi square, okay, which is equal to what? In this case, this is equal to this number. Okay. All right. So we have calculated the computed value of chi square. What do we do next? Next, we find out the standard chi square value depending upon the degrees of freedom and the significance level. Okay. So let us do that. What are the degrees of freedom in this case? Degree of freedom is what? It is nothing but k minus p minus 1, right? What is k? K is the number of classes, which is what? 7. What is p? P is the number of parameters. How many parameters are there in the exponential distribution? Only 1. Minus 1 is equal to what? 5. So 5 is the degrees of freedom. Okay. And then say let the significance level be 0.05. Okay. Now what we do is we go to the standard tables of chi square. The chi square tables, the chi square distribution tables will be available in any standard book on the statistics. Okay. You take up any probability and statistics textbook, at the end you will find lots of tables corresponding to various distributions, and one of them will be the chi square. All right. And it's a two-dimensional table in which the chi square value will be given depending upon the degrees of freedom and the significance level. So you just read it off the proper one. Okay. So if we go to those tables, what we will find is that your chi square for 5, 0.05, okay, will be equal to what? It will be 11.07. Please verify that. All right. So is the test pass or fail, or is the fit good or bad? What was the condition? The condition was if your chi square nu comma alpha was greater than the chi square c, means what? Good fit, isn't it? Right? What do we have? We have the computed, no, the standard value goes here, it is 11.07, right, is greater than, what is the computed value? Let me go back. The computed value was 3.37 something. So let me say 3.4. It is 3.4. Means what? It's a good fit. Okay. All right. So what is the conclusion of carrying out this chi-square test? Well, there are various ways of saying it. Okay. One of them we will say is what? The hypothesis that the data come from the exponential distribution cannot be rejected. All right, cannot be rejected at 5% significance level, okay, or you can say 95% confidence level, any of these two things. Okay. Another way of saying is that same thing, the hypothesis blah 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 blah, same thing, I am not going to write it again. Then you say is accepted. What is the hypothesis? That the data come from the exponential distribution or the data follow the exponential distribution. Is accepted at what? At 5% significance level or 95% your confidence level, okay. Or simply you can say that the data follow the exponential distribution at alpha is equal to this or confidence level is equal to 95%. Okay. So, you see that this way we have seen how we can carry out or how we can conduct the chi-square distribution test or chi-square test. Any test we take, all we do is we compute a test statistic based upon the data. Other one we find out which is called the standard statistic and then we compare the two, okay. And if the computed statistic is less than the standard value, okay, in this case we saw the standard value at degrees of freedom and different parameters. If that is more or the standard statistic is more, then we have a good fit, otherwise we do not have a good fit, and then there are various ways of actually saying that. Okay, I would like to stop at this point of time because I am running out of time, and then what we will do in the next chapter actually is we will start with the frequency analysis. Okay, thank you.